Hi there, thanks for joining me this evening. I'm inside this evening. You usually see me outside in my outdoor kitchen, but here's my indoor kitchen, 1989, Korean countertops, 1989, blue tile back here. Welcome to my kitchen inside. So today what we're going to do is wire up this circuit, and this circuit I'm going to kind of give you a surprise of what this circuit is. You'll see that we only have two inputs, A and B, and these inputs are going to a NAND gate and then another NAND gate, another NAND gate, and another NAND gate. 1, 2, 3, 4 NAND gates. You'll learn later on that we can actually replace any of the basic plain, 3 circuits and or not the basic circuits. We can actually represent any combination of those basic circuits just with NAND gates. So that's a concept called universality of NAND and NOR. But today we're not going to talk about that, but you are going to see today, kind of in a backwards way, that this circuit made out of NANDs can be made out of basic components and not. So the question is, how do I build this circuit with all of these NANDs if I only have an inverter, an AND gate, and an OR chip, an OR gate? An OR chip, which has 4 OR gates on it. The AND has 4, and the inverter has 6. So this is all we have for to work with is a NOT gate. We have an and we have an OR chip. And the question is, how do we build this circuit? Well, we're going to use our Boolean algebra, and we're going to look at the relationship between the inputs and the outputs on in a Boolean algebra way. So let's take a look and write this as a Boolean expression. So the first step would be to write this as a Boolean expression. I do that by looking at the output first, and I say that output, call it X, is coming out of this NAND gate. What does a NAND gate look like on paper? A NAND gate looks like this on paper. It has something ANDed with something, because the symbol for AND is either this or just like this. This is AND. It's like multiplication in math. The Boolean symbol for OR is like this. And the Boolean symbol for an inverter is this big bar. This is not. So a NOR gate is it's a NAND gate. A NAND gate is a dot or just brackets beside each other with the inverter over the top. So there's the structure, and it's already looking a little Boolean equation-y. Now I look at, okay, what's the easiest thing to go in there? They're about the same. Let me look at this one. Inside this input, I see another NAND gate. So I'm going to do the structure for another NAND gate. It's inverted. It has something going in and something else going in. What went in? A went in. What else went in? Ooh, the combination of another NAND gate went in. Structure of the NAND gate. Structure of the NAND gate. What's inside that NAND gate? A is NANDed with B. A, B. Looks ugly, but I think it is technically correct. Now, on the other side, all of this goes into the NAND gate. It's another NAND. It's another NAND structure goes in there. It has one input and another input. One of the inputs is simple. It's a B. The other input is a whole NAND gate. Put in the structure for that NAND gate. What goes into the inputs of it? A went in and B went in. A, B. This is an ugly Boolean expression. So let's simplify it. I mean, I'm not simplifying it, I'm just rewriting it to make it look better, because I have a few too many brackets in there that I don't need. I still have too many brackets. Ooh, that wasn't really written that nicely. And everything went through that inverter. I see it right there, everything going through that inverter. All right, so it has to have this line all the way out across the top. Now, that doesn't really help me very much. I can build all this. Now I see that I can do some things. I can have AND gates. I can use my AND gates that are in here. I have 4 AND gates in each chip because this is a quad AND gate chip. But how many would I need? 1, 2, 3, 4, 5 AND gates. So I still can't build this. I only have 4 AND gates inside this chip. So therefore I will simplify. So let's simplify this. I would probably use De Morgan's theorem. De Morgan's theorem says I can break up this big inversion bar that goes across both of these if I change from an AND to an OR. So let me put in the structure. I change the structure from an AND, which is a dot, to an OR, which is represented in Boolean algebra by a plus. If I do that, I can break up these bars. All De Morgan is saying, you really have to prove De Morgan's theorem yourself to really believe it. But it says that this is equivalent to an OR. So an AND that's inverted afterwards is equivalent to an OR that is, each input is inverted beforehand. Those are equal to each other. That's what De Morgan says. You can prove it yourself with truth tables. And that's a good exercise. So now we have the same thing on either side. It's that same kind of ugly pattern there. But De Morgan has helped us break up that top bar. Now it's broken up. And now I have bars of equal length here. And we know that that means we have a value, call it y, going into an inverter and then coming out of that inverter as y bar, and then and then it's getting inverted again. So then it comes out as y again. So really double inversions that are of the same length there just cancel each other out. So I'm left with this. All right, now if I look at this separately and this separately, what if I do De Morgan's theorem again on that? And again, I say that this NAND situation is the same as 2 inverted inputs going into an OR situation. So that is true. So let me do that. Perform De Morgan's, change the sign, break up that bar, same 2 inputs. Change the sign, break up the bar, same 2 inputs. And then B went along for the ride. All right, good. That's fun. Now let's distribute across, because we can do distributive law in Boolean algebra as well as regular algebra. We want to keep things in alphabetical order. And now I think about this. I don't say this goes to 0. I think about it and I say, this is an AND gate. It's going through an AND gate. And an AND gate is only going to have a high input if both inputs are high. Well, obviously both inputs are not high here. A is equal to 0, then A bar is equal to 1, or A is equal to 1 and A bar is equal to 0. Therefore, the output of this particular term in this expression is going to be 0, because A and A can't both be 1 if it's an invert of an A. So I like to put that line there just to understand that it didn't equal 0 in the numerical sense of counting, but the expression results in a 0, and 0 or anything is the anything that you put in, because if anything is 1, the answer is 1. If anything is 0, the answer is 0. So 0 or anything results in the anything. That is another one of our Boolean theorems. So this is what I'm left with, which traditionally is usually kind of written like this, just with the inverted signs on the outside. It's just often written like that. So what we have here is a pattern, and this should be a recognizable pattern. So anybody studying Boolean algebra should be able to recognize this pattern. This is a pattern of basic gates. We don't have to recognize it as a pattern, but it is a very useful pattern to recognize. And it's a pattern that we call exclusive OR. The pattern of exclusive OR basically says, it says we have stars and hearts, or stars and hearts, and if one side is inverted and the other input is inverted on the other side, then it is an exclusive OR pattern. And we have a symbol for exclusive OR, and we put our stars on one side and our hearts on the other side. All right. So there's that pattern. I see that my stars are A's and my hearts are B's. It could be apples and oranges. It could be anything you want, but there's AB on one side, AB on the other side. A is inverted on this side. The opposite one's inverted on this side. B is inverted on this side. That's a pattern I should recognize. We as humans have said that's a pattern to remember. We like to give it this symbol for exclusive OR. And what that pattern says is that it's like an OR gate. In an OR gate, the output is high if one or the other or both are high. But in an exclusive OR gate, then the output is positive if one or the other and not both is high. So the exclusive OR excludes this 1-1 case. This 1-1 case is excluded. Exclusive OR is kind of a mean gate. It's an excluded gate. So anyway, in conclusion, this circuit that you see here with NAND gates that I could not build because I only have an and or not gate, basic gates, is actually this, which is equal to this, which is equal to this, which is equal to this, which is actually equal to this cheap gate that is an exclusive OR gate. Now, here's the two ways you can build it. You can go over here and get this extra gate. You see, I have my NOR, my NAND, and my OR, but then I just went over here in the Magic Kitchen and I got this one. It's an exclusive OR gate. I actually have an exclusive OR gate. Do you? Because if you want to just wire this with an exclusive OR gate, then all you have to do is look up the pinout for an exclusive OR, and I can tell you there's 4 ORs in there: input, input, output, input, input, output, just like an AND gate, OR gate. So you can easily wire that up just like an AND gate. Input, input, output, that is your exclusive OR gate, and it will perform the exclusive OR function. That's one way that you can wire it if you have that gate. But do you have that gate? I feel very special over here. I have that gate. But what if you just have basic gates? That's the point of this video. If you just have basic gates, then I can build it with this pattern here and with my basic gates. So let's do that. I have these gates. I have an inverter. This is not. I have and an OR. And what I like to always tell you is if you don't know how to wire something, then the thing that tells you how to wire it is the pinout. So let's look at the pinout for, let's say, an AND gate chip. It's not a secret. It's not only me who knows it. Here's a pinout for an AND gate chip. It goes in, out. There's 1, 2, 3, 4 gates in there. All right, so I would probably just wire up this AND gate. I would have A coming in to pin 1. I would have B coming in to pin 2. I would have an output going into an OR gate. OR gate is wired the same way. It's just ORs inside. In, out. Pin 1, 2, 3. So I would put the output of my AND gate into pin 3 here, of my OR gate into pin 3. And then I would do the other AND gate, which is down here, pin 4, 5, 6. Pin 4, 5 are inputs. 6 would come over to be the pin 2 OR gate input. The OR gate is what goes to an LED, and the LED is going to go to ground. Now, the inputs, I think I'm just going to have an A, and I'm going to have a B as inputs. I'm going to bring A and B in to get knotted by plugging them into this row, which is all electrically connected. So I'm going to inverse them, and when I inverse the A, I'll take a wire down and put it in my first AND gate. Inverse the A, put it in the first AND gate. And when I inverse the B, I will take a wire and I'll stick it in my second AND gate. All right, into my second AND gate. And then I will just take a plain old A from somewhere else in this row of terminal connectors that are connected to each other. And I put the A in here, and I'll put a regular old B in, up here. And I think that's what I'm going to do. I also have to plug in power and ground. Pin 14, pin 7, power and ground, pin 14, pin 7. I will have to do as well, but this is how I solve this Boolean. This is how I write down the Boolean expression. I simplify the Boolean expression using some Boolean theorems. I recognize that the pattern is an exclusive OR. I go and I grab my exclusive OR chip if I'm lucky, because I have one, and I just wire it like a simple AND gate, pin 1, 2, and out. And that would make my life easy, but I'm going to pretend I don't have this exclusive OR chip, and I am going to wire it with basic gates. I'm going to use an inverter to invert my A and B inputs. Then I'm going to steal those same inputs. I'm not going to make new inputs. I'm going to steal those same inputs. I'm going to put them in my other AND gate. So these two in one AND gate, these two in the other AND gate. From the AND gate, I'm going to OR them. Each AND gate becomes an input to an OR gate, and then it comes out and it goes to the LED. I want to wire that. Let's actually do that. First step is we have to make sure that this is, that our breadboard is upright. All right, our breadboard is upright, and then we are going to put our AND gate. We're going to put our OR gate. And we're going to put our NOT gate on the board. There we go. Now I'm going to wire some inputs in. Those inputs are going to be, there we go, 1, 2, and those inputs are going to be A and B, and I'm just going to put them along here for now. And if I plug those in here, then they actually will bring power, or they'll bring whichever signal I want. I can just actually leave them out. They'll bring whichever signal I want to that whole row. So those are my inputs. I want one of those inputs to be inverted. Oh, whoops. So that's an inverter, and I want that to go down there.